Time for us to get started. So this is our annual Sackler lecture, to which we invite a distinguished senior colleague to come and visit for a few days and get to meet as many of us as possible. And also to give us a lecture, which is what we're here to do tonight. Our Sackler lecturer is Dr. Ken Freeman. Ken is a native of Australia. He was educated in Western Australia in mathematics and at the University of Cambridge in theoretical astrophysics. He postdoced at the University of Texas at Austin and also at Trinity College in Cambridge before returning to Australia. And he has played a dominant role in Australian astronomy ever since, and a very, very significant role in international astronomy, especially astronomy of globular clusters and of galaxies. He's credited justly with a number of very significant successes, but he was very early to realize the significance and, in fact, the very existence of flat rotation curves in spiral galaxies, which led to an abiding interest on his part in dark matter, which grew out of that early work on the dynamics of galaxies. I've known Ken for a long time. We actually worked very closely together on microlensing during the 1990s, which was a lot of fun. And but whereas for me it was maybe the most significant intellectual experience I've had in my career, it was just one of many intellectual experiences in Ken's career. He's been recognized in many different ways. He was the Henry Norris Russell Lecturer of the American Astronomical Society in 2013. He shared the Gruber Cosmology Prize in 2014. He became a Fellow of the Australian Academy of Sciences in 1981 and of the Royal Society in 1998, and a Foreign Associate of the US National Academy of Sciences in 2017, and a Companion of the Order of Australia. That sounds kind of big, though I don't know, in 2017. So with that, I think I'll just hand the floor to Ken, and he's going to talk about baryons and dark matter in galaxies. Ken.
Well, thank you very much, Charles. That's a nice introduction. One second here. Okay, so my subject today is baryons and dark matter in disk galaxies. And so what we're really trying to understand, these sort of galaxies give us one of the most direct indications of the dark matter distribution in galaxies, but there are a whole bunch of pitfalls in actually trying to achieve that. So first of all, the people who've collaborated with me in this exercise, just to mention a couple of them. Surya Anian is a graduate student who is now finished, and she did much of the work I'll be talking about. Anastasia Ponomareva is my postdoc, and she's also done a lot. And these other people are, some of these are, very serious people in their own rights. And I've also worked quite a bit with John Cormandy on this general project in dark matter. So the problem is the way we try to get information about the matter distribution in dark halos. It's based on rotation curves. And here's a couple of examples of rotation curve decompositions. This is velocity of rotation against radius in this particular galaxy, well-studied galaxy. The black points in the curve show the actual observed rotation. The red the red curve is the contribution of the disk of the galaxy, and the green curve is the contribution from the dark halo. And the way it works is that you try to estimate the contribution from the luminous material, and that's really what this talk is about. And then the rest of it comes from the dark halo. And you can see straight away, even in this decomposition, that the rotation that you see out at large radius is much smaller than the rotation you expect, or that you actually observe. So this is the contribution from the disk, much smaller than what you actually observe. The rest of it you make up with the halo. But the problem is that there's a degeneracy here. Unless you know something more about the disk, I mean, we know the shape of this rotation curve because we assume that the mass of the baryons, the stellar baryons, follows the light, but what we don't know is how to normalize it. And that's the degeneracy. And just from the rotation data, we don't really have the information to do this uniquely, because you can see that both of these are fairly acceptable fits. The curve is the quadratic sum of these two, and both of these solutions give you quite an acceptable fit. But you can see that here, the rotation of well, it's really the gravitational field of the baryons is quite a dominant component, whereas here it's quite a small component. This greatly affects the properties of the dark matter halo that you infer, but we've got to find a way of breaking this degeneracy. So we know the shape of the disk rotation curve from surface photometry, but we don't know the amplitude, just how much to scale this. To break this degeneracy, we have to measure somehow the surface density, sigma, of the stellar disk. In other words, we've got to measure how many solar masses per cubic parsec at different radii there are in this disk. Now, to measure the surface density, there's a method that's been evolved, that's been much used, and we do it by measuring the random vertical velocities of stars in a disk, and we measure the scale height of these disk stars. And then the surface density is proportional to the random velocity squared divided by the scale height. And these are both in principle measurable. But you can see that it makes an enormous difference what we actually ascribe to this disk. Makes enormous difference to the halo. Now, one of the things we want to know about halos is what is the density of the halo in its inner parts. Now, that density, we can derive that almost directly from the green rotation curve that we infer from the halo. It's really just proportional to the square of the slope of this rotation curve. Now, you see, it makes an enormous difference which one of these stellar disks we adopt, because here the rotation curve for the halo is very steep, so the density is very high. Here it's quite shallow. And we can also measure a scale radius for the dark halo, which we get from the curvature of this halo rotation curve. But the two disks that I've shown here, this rather dense one and this not so dense one, they give dark halo densities that differ by a factor of 20. So it really matters for what we understand about dark halos, which one of these things we adopt. Now, this sounds very simple. You measure a random velocity of stars in the disk in the vertical direction divided by the scale height, but there's a conceptual problem in measuring the surface density of the disk, and that's really what a lot of this talk is about. So, the sort of galaxies that we can do rotation studies on are things like this. They've got a lot of gas, but because they've got a lot of gas, they also usually have a long history of star formation. So we expect to find kinematically cold material, stellar disks, young stars, which are moving almost in circular motion and only vibrating just a very small amount vertically to the disk. And on top of that, we find the old stellar disk that's been there for giga-years, and that we know, and I'll show you in a moment, that's a much hotter stellar population. To get the surface density of the disk that we need to decompose the rotation curve, we need the scale height, just the vertical extent of the disk, and the velocity dispersion. Now, the scale height comes from surface photometry of not of the galaxy that we're actually looking at. We have to look at a face-on galaxy to measure the vibration, but of course we can't measure the scale height then. We use similar galaxies that are seen edge-on. And here's an example of what this galaxy might look like if we were looking at it edge-on. We measure the scale height from surface photometry of systems like this, and when we do that surface photometry, we're actually avoiding this dusty layer and the young stellar population that's hiding behind it. On the other hand, when we measure the velocity dispersion, the random velocities, we do that from spectra of near face-on disks like this one. And when we take an integrated spectrum down through the disk, we get everything. We get the young population, which is moving quite slowly, and the old population, which is moving fast. And when we combine this, we really need to be combining scale heights for the same population as we're measuring velocity dispersions for, and therein lies the problem. So the conceptual problem is that for estimating surface densities, the scale height and the velocity dispersion must be for the same population. If you don't have the same population, you're going to get the answer wrong. As I mentioned, the scale height can't be measured from face-on galaxies. We have to use surface photometry of edge-on galaxies and then estimate the scale height for our galaxy, the face-on one, from a relationship which has been pretty well established now between scale height and scale length, which we can measure. The surface photometry, as I mentioned, avoids the dust lane, and it's weighted to the older disk stars away from the disk plane. The velocity dispersion comes from spectra integrated vertically through the disk, with a significant contribution from the slowly moving younger disk stars. And here's the problem involved in this. This is how the stars in the neighbourhood of the Sun move in the vertical direction. So sigma W is just the typical vibration velocity of stars of different ages. So here, the young stars, we see have a vibration velocity near the Sun of only about 10 kilometres a second. As we go to older and older stars, these have been around longer. There are heating processes which we don't properly understand, but this is just an empirical relationship. And you see that the old stars, say between 5 and 12 gigayears, they have velocity dispersions around a bit over 20, whereas these young ones are really moving quite slowly. Now, stars are born with low velocity dispersions, as we see here, around 10 kilometres a second. This increases with age due to these uncertain heating processes up to about 22 kilometres a second. Now, for other galaxies, as I've said, scale heights are measured away from the central dust lane, and they really pertain to these older, hotter, kinematically hotter stars which get up into these regions that you're measuring. On the other hand, the velocity dispersions are measured from the integrated spectra of the young and the old disk stars. The young stars, although there's not a vast number of them, they're very bright, so they make a large contribution to the light. So what happens then, you are measuring a velocity dispersion not for this population, which is what you would like, but for all of this mixture, which has a significant weighting to these slowly moving stars. And the result of this is that you are underestimating, when you take the velocity dispersion squared and divided by the scale height, you are underestimating the surface density of the disk. Now, this procedure for measuring surface density of the disk it started in 1984, and I was involved in this with colleague Pete van der Kraut, and people have always found that the disks are rather submaximal. In other words, that they're like the low density decomposition that we saw. And all observers since 1984 have done what I've basically outlined here, mixing scale heights for old populations and velocity dispersions for all the populations. So what are we going to do about this? So anyway, here's the sort of major studies in this. We did this for integrated light of disks. These other people, they also used integrated light. A big study here, a very nice study, but you're doing the same thing by Bashady and others. Many papers have come out on this. It's called the Dismaster Project. And Herman and Chardulo used Planetary Nebulae, as we will in what I'm about to tell you. But anyway, everybody who's done this have found low disk surface densities, concluded that the disks are submaximal, and this, of course, skews what we estimate then about the dark halos. So how can we do this correctly? The problem of contamination of young stars, it affects any dynamical tracer whose progenitors can have a large range of ages. So it affects red giants, which dominate the integrated light, and also planetary nebulae. Planetary nebulae are good dynamical traces, as we'll see in a moment. So we need to find a way to measure the velocity dispersion of the old hot disk stars without the contamination from the young cold disk, and that's really the goal of this project that we're still in the middle of. So we started this project with a pilot study of stars in the solar neighbourhood. We just wanted to see if we were observing the solar neighbourhood from outside, how wrong would we get it? So anyway, we made a quantitative estimate based on the kinematics of young and old red giants in the solar neighbourhood, and that indicated to us that the surface density of galactic disks has been typically underestimated by this method by about a factor of 2 because of the effect of the young cold disk. Now I can show this to you sort of graphically. This is a colour magnitude diagram of a population, just a theoretical population near the Sun. In red, I'm showing stars that are younger than 2 gigayears, and in black we see the old population. So you can sort of see where the young giants, for example, they're the important ones for us, where the young giants lie. They go down to a luminosity here of about absolute magnitude +1, but they do extend a long way up to the bright end. Now let's have a look at the vertical motions of stars near the Sun. These are giant stars, which would be in this region here. You can see that there's a big velocity spread for these fainter, older giants. The young, bright giants, you see that they have a very small velocity dispersion, just reflecting what I've been telling you, that these young stars only have a small velocity of vibration. Now, if we were to integrate all this up, we would get quite a big effect from these because these are so bright. There's not many of them, but they're very bright. And here's how this worked out quantitatively. We're now looking at a velocity distribution for about 1,500 red giants in the solar neighbourhood. So this is just the number of stars against their vertical velocity. And if we were just to analyse this as a single Gaussian component, we would get this the fit shown by the blue curve. If we were to look for two components, a cold one and a hot one, we would get what we're seeing in the red components. This is the cold component here. This is the hot component. And when you add them together, you get something that really fits the wings a lot better. But the interesting thing is the actual numbers. If we do a one-component analysis, we think the vertical dispersion is about 13. If we do a two-component, we get 9.6 for the cold ones, but we get 18.6 for the hot ones. We keep the hot ones. We throw this one out because we're really not dynamically very interested in these for this exercise. But you can see what we should be combining with the scale height is this number. What people have been combining is that, and that's worth a factor of 2 in the surface density. So having done that study in the solar neighbourhood, we then have gone to new observations of nearby almost face-on close to face-on galaxies, and the goal is to measure the vertical velocity dispersions of the hot and the cold disk components separately. Once we've got the cold one, we don't use it, but we do use the hot one. Here are the two galaxies. This one's almost perfectly face-on within a few degrees. This one is a little bit more inclined. So I just want to talk now a little bit about this. So what we do, we have two ways of measuring these surface densities. We need a scale height, which we get from elsewhere, and we need random motions. So the first thing we do is to do it using integrated light techniques, and then we check it with a quite independent study of planetary nebulae. The planetary nebulae are really just evolved red giants, but because a significant fraction of their light comes out in one emission line, we can measure quite accurate velocities for individual stars. And in fact, you can measure individual stars out to 100 megaparsecs, which we don't need to do here, of course. Okay, so what we do is we measure the random motions for the young population and the old populations in the young disk and the old disk by using integrated light spectra in these two galaxies. And for doing that, we use an IFU spectrograph called VIRUS-W on the 2.3 or 2.7 meter McDonald telescope in Texas. We combine this data with radial velocities from several hundred disk planetary nebulae. Now, some of these disk planetary nebulae are young and some of them are old, but we do a related study, but we use a machine that we built that we use on the Herschel telescope in La Palma. I'll tell you a bit more about that as we go. And then, having gotten the dispersion for the old population and the scale height for the old population, we can now we believe, derive these surface densities more correctly and then go to decomposition and study our dark halo. Okay, so the model for the old disk, I like doing stellar dynamics, and this is a cute little exercise in stellar dynamics. We use the old disk as a tracer of the gravitational field. So just as I've been saying, we estimate its scale height and we measure its velocity of dispersion. And we need a model that tells us how the velocity of dispersion actually changes with radius. But we can assume that the scale height doesn't change with radius for late type spirals. There's a nice study done some years ago that established this. So to derive the surface density from the scale height that we measure and the velocity dispersion that we measure, we need a dynamical model. And here's an example of a couple of dynamical models that have been used a lot. One is that you use an isothermal disk. That just means that the velocity of dispersion doesn't change with height. And you can find an exact solution for that. And the density has got this form. The density goes like Sheck squared of z over 2 times the scale height. Or you can take a disk that's exponential in height. That's slightly more complicated. So the density dies off exponentially. That's pretty much how they look. And then you can get the surface density from a factor f, which is just the geometric factor, 0.16 or 0.21 sigma squared divided by g times hz. Okay. The cold layer of gas and stars can actually be quite a big fraction of the total surface density, particularly in the outer parts of the galaxy. And we'd like a simple model that includes the gravitational field of both the thin layer of cold gas and stars and the older, hotter disks. And that's, up to this point, people have mostly used one or the other of these two, which really ignore the gravity of the gravitational field. But that can be quite significant. So, in the famous book by Binney and Tremaine on galactic dynamics, problem 422 actually provides a model for us, but the only trouble is they don't give you a solution. And we had to actually solve this problem, and it turned out to be harder than it looked. Anyway, I think we did it. So, determine the density of an isothermal distribution of stars with velocity dispersion sigma z. Okay, so that's almost the same as the Sheck squared. But it contains a thin layer of gas in the midplane, and that's got surface density sigma c, and that's sigma for cold. Now, I won't go through the gory details of the solution, but it comes out rather much like the Sheck squared that we had for the plane isothermal, but the effect of this cold layer is it offsets the origin of the Sheck squared just by a constant, and the inverse tan of that constant, which is, if it's small, is pretty much the constant itself, is just the ratio of the surface densities of the cold component to the total component. And the total density, the sigma d is the hot stuff, hot stars, sigma c is the cold stars and gas. It's just the same sort of formula that we had before. And this is the model that we use. So as the fraction of cold stuff to total stuff increases in the disk, and this offset B increases, the density distribution that we've got here actually tends towards the other solution that people use a lot, which is the exponential. And that's just a sort of interesting thing, and I just want to show you that because it's cute. So here's log of the density in a disk, and we're just going up through the disk vertically. This is the Sheck squared that we have if we just ignore the cold component. This is what happens for a situation where half of the surface density is cold and the other half is not. So that's this thing here. And you see that's really approaching quite closely to the exponential, which is the blue one here. So just an interesting thing for people who like this sort of stuff. All right, so here's the model. We use this one-dimensional isothermal model, one-dimensional in the vertical direction, solving for a combined thin, cold, or young, and hot, old disk. And the model is actually an analytical solution to the Boltzmann and Poisson equations. So here's this green thing is meant to show the hot isothermal layer. It's got a scale height hz, integrated velocity dispersion, sigma z, so we integrate right through this thing, but it's, by construction it's isothermal, so that's a pretty easy integral, and the surface density is called sigma d. And then we have a cold, very thin layer of gas and stars with a surface density that's sigma c, and that's partly gas and it's partly the young stars. So the hot layer is a dynamical tracer of the total surface density. That's the thing we're after. And it's just a simple formula, cold stuff plus hot stuff. It's just this velocity dispersion that we measure for the old component divided by 2 pi g times the scale height for the, oops, the old one. Okay, so I just want to tell you a tiny bit about the instruments. They've really been quite critical for making this work. In this telescope here, this is the 107-inch telescope at McDonald Observatory, and no, it's not. Oh, it is, sorry. So in here, there's this Virus W spectrograph. It's an IFU spectrograph. It was built by Max Planck Institute and the University in Munich to go on a mountain just south of Munich, but it's being used at the moment in Texas. It's an IFU spectrograph, 267 fibers, quite a nice field, but the important thing, it's got high resolution, and we need high resolution to measure these rather small dispersions, velocity dispersions, that you get in the disks. So the PSF has got a Gaussian sigma of about 15 kilometers a second, and with that it's fine if we have good high signal to noise spectra. We can measure velocity dispersions down to about 10 kilometers a second, and that's all we need. We need high signal to noise to do this, and this spectrograph is very well designed to do this sort of high resolution spectroscopy at low surface brightness. We've also got some data from a somewhat similar instrument in Australia, which we haven't fully analysed yet. So this is what the data looks like, or at least the layout of the data. The IFU itself, this is the IFU, one of these rectangular regions. These little circles in here, they are the fibres of the IFU. So at every point in this configuration, we get a spectrum of a resolution of about 8,700. So we have these various configurations where we put the spectrograph and we have to measure the sky and all that sort of thing. And for the reduction, we finished up partitioning it into 2 bins inside this circle. So we just take all the fibre spectra inside the circle and outside this circle, and we'll see those in just a second. For the planetary nebulae, we, around nearly 20 years ago now, we built an instrument. We were doing work on other sorts of galaxies, and as I mentioned, extragalactic planetary nebulae are terrific velocity tracers because you can measure their velocity so accurately. But there's a nuisance factor there, because usually to find planetary nebulae in other galaxies, you have to do an imaging pass through a narrowband filter, find the things, and then go back to the telescope time allocation committee again for more time, but this time for spectroscopic work. And we thought we can probably do all this in one operation, and we designed this instrument to do exactly this. As a group of us got together, and we've been using this thing for the best part of 20 years now. It's a counter-dispersed imaging spectrograph that lets us find planetary nebulae and measure their velocities in a single observations using this bright emission line of oxygen-3. Before that, we had this 2-pass technique that was very, very annoying. The instrument we built also has an imaging arm in H-alpha to help us separate ionized gas regions, H2 regions, from planetary nebulae, and you'll see why that matters in just a second. So here's the instrument. Light comes in here, passes through the instrument. There's a narrowband filter here, so we don't get light other than what's coming from the line. And then here, the instrument forms a pupil, and there are 2 gratings. Half the light hits this grating and goes to this camera, and the other half hits this grating and goes to this camera. And the outcome of doing that is an image that looks like this. So this is one of our galaxies. When we have a star in the field, it comes out as a narrow streak, and that's because the spectrum has been dispersed, and it's cut off by the narrowband filter. So we get all the, when you see these streaks, you know that that's a star or something with a continuum. So emission line objects like planetary nebulae or H2 regions, they appear pretty much just as dots. Lyman alpha emitters are our background contaminant. At the redshift very close to pi, they appear also as dots, and they're a real nuisance factor. So we look for objects that are unresolved as possible planetary nebula candidates. Now, some of them are H2 regions, but a lot of them are planetaries. So so this is just one of the two images. So remember, we had two images from the split pupil, and when we combine those images, this is what we get. Okay, so we register the two images on the stellar spectra. And I'm going to show you in just a second that between the images, things like the planetary nebulae, they actually shift. Well, let me just do it now. Okay, so the stars aren't moving, but you can see that the dots do move. And the shift there is a measure of twice the Doppler shift. And it turns out that you can do this really, really quite nicely. The accuracy of this thing, or the precision, is actually pretty good. This is a magnitude in this 5007 line. Here's the error in the measurement. Our planetaries in the galaxies we're looking at are to the right of this vertical line, so they're relatively faint. But you can see the typical errors are around 6 to 8 kilometers a second, and that's very good. We have to do some things to the software for this thing, but anyway, it's producing quite accurate radial velocities. So in each of these galaxies, we find several hundred planetary nebulae, and we can use those for doing the kinematics. Okay, so here's the just show you some results for the two galaxies. So this is our first galaxy. It's a beautiful thing. It's almost perfectly face-on, about 9 megaparsecs away. We have planetary nebulae and virus W data. To reduce the data, we get rid of the galactic rotation using H1 velocities from a VLA survey at the location of each planetary nebulae that we find and at each IFU fibre. And that gets rid of any velocity gradients across the field. Here's the virus W image again. I think we've seen this one. So we combine all the points outside the line and the ones all inside the line to give us two values for the velocity dispersion. So looking at the analysis of the spectra, these are our high resolution spectra, and what we're seeing is the red, which is which, yeah. This is actually a plot of two spectra. One is in black and one is in red. But the black one shows you the actual observations, and here we're getting a few local emission lines which we don't use. These are magnesium lines. These are iron lines, and it's from the broadening of those that we get our velocity dispersions. These two things in green, well, you can see the black and the red are almost perfectly overlaid, so the best fit and the observations really come together quite well. The two individual components, hot and cold, are in cyan, and we use a program by Michele Capillari called PPXF for doing this, which works fine. I think there are probably better ways of doing this, but we haven't developed those. I think we can see what to do, but we haven't done it. You may be able to see that one of these spectra looks very slightly sharper than the other one. I won't tell you which is which, but you have a look and see if the code actually does pick up that one of these is actually rather sharper, and one is the cold component and one is the hot. Then we've got the planetary nebulae. We have about 700 of those. Some of them are planetary nebulae, some of them are H2 regions, and we use a colour magnitude relation between the O3 magnitudes, the oxygen line, and the H alpha magnitudes to discriminate between planetary nebulae and H2 regions. And this is sort of how it works. I mean, we know that there's a maximum brightness for planetary nebulae. There's been a lot of work done on that. In our galaxy, that maximum brightness is about here. So these things are mainly planetary nebulae with some H2 regions, but we can be pretty sure that these things here are just H2 regions and we don't want to use those. Other people have studied the planetary nebulae in these galaxies, and we use their studies to throw out H2 regions. And the criterion that these people have developed, they look at the ratio of O3 to H alpha, and they put a line here, and objects to the right of this line are mostly planetary nebulae, and these are mostly H2 regions. I won't go into too much more detail. I'm happy to answer questions on it. So in the end, of our 700 objects, about 400 are planetaries. We derive velocity dispersions in 3 radial zones, each with 135 planetaries. We use a maximum likelihood method to dig out 2 dispersions from the data here. And so this is the end point of a study like this. We look at the vertical velocity dispersion as a function of radius in this galaxy, NGC 628. Here are the 2 points from the IFU. Here are the 3 points from the planetary nebulae. This is the hot component. That's the thing we really want. If we do a 2-component analysis, we get a cold component out, and you see it's around where it ought to be, around 10, 12 kilometers a second. We found this thing and we throw it out. And these other things I won't go into much, but they're just to show that our planetary nebulae results agree quite well with what other people have done. Okay, so similar things for the other galaxy, NGC 6946. I won't go through the details there, but it turns out a very similar looking diagram for these 2. Here's our 2 IFU points. Here are the 3 planetary nebula points. You see that the velocity dispersion decays away as you go into the outer parts of the galaxy because the vertical gravitational field of the disk is dying away. We know how it should die away, and we fit this curve to it, which is actually a pretty good fit. And from that, we derive the quantities that we need to measure the velocity, the surface density of the disk, but just using the hot velocity dispersion. It makes a big difference. Okay, so here's a summary of what we got. Here are our 2 galaxies, rather similar absolute magnitudes. This one is forming stars at about 1/4 of the rate of this one. Here are the velocity dispersions in the middle. Central density, total density, this is hot and cold and everything. Scale heights that we adopted are actually pretty similar. Scale lengths turn out to be pretty similar. Dynamical ones pretty similar. But the important thing is this last result. This tells us the mass to light ratio of the disk of these 2 galaxies at 3.6 microns. And we use 3.6 microns because there's a large amount of very good photometry for galaxies that's been done from the Spitzer spacecraft with Giovanni Fazio as the lead. But what you can see is that the mass to light ratios that come out of this are fairly similar. The highly star-forming galaxy has a slightly lower mass to light ratio. And these mass to light ratios have been corrected for inclination and for extinction. So this slide shows you how our results compare with what people have done in the past, particularly the big Dismaster study, which is really a very nice study, but using just single components. This shows you some synthetic mass to light ratios for synthetic spectra from 2 different sources of isochrones. I've just used this one here. The K-band data is the K-band mass to light ratios are in blue. 3.6 ones are in black, so they're not very different. Our mass to light ratios are in the range shown by this box in the vertical direction. This is what the Dismaster people have got, and it is pretty much, again, as we saw, it's around the factor of 2. So now we can do the rotation curve decompositions for these, because we've now got actual surface density values for the hot and cold stars and the cold gas in the disk. Any shortfall is due to the dark halo, and we try different dark halo models, and the pseudo-isothermal models that most observers use are marginally better than the NFW ones. Decomposition is difficult for our first galaxy because it's a bit face-on, and you'll see the results don't look too fantastic. This one is more inclined. The disk that we see is clearly maximal, has a slightly lower mean mass to light ratio, and star formation rates about 4 times higher. So here's the NGC 628 data. This is just in this one. I'm just showing the total disk surface density. This is the observation, so we don't have any freedom now in moving this thing around because we've measured it, and this is the halo, sort of halo that we need. But you can see this is very ragged because we have to put a big correction on because it's so nearly face on. This galaxy is better for this purpose. Here's the 21 centimeter data. There's a little bulge in the center, but the total baryons, we add together the hot stars and the cold stars to get the red curve. Here's the contribution from gas. There's a lot of gas in this galaxy. So here's the total baryon rotation curve, and you can see that the baryons are really dominating the potential field in the inner parts. But once we get out to about 10 kiloparsecs, the dark halo kicks in and is really contributing most. And so this is really the end goal of what we want to do. And I think the indications are pretty clear that the dark matter is not dominant in the inner parts. Okay, so conclusion so far. Conclusion so far. The disk halo degeneracy in rotation curve decompositions can be broken by dynamical measurements of the disk surface density, but in this method, the scale height and the vertical velocity dispersions must both pertain to the same population, and we are using the old disk stars. The disks of our 2 galaxies are maximal. The mean disk mass to light ratios are around about 0.5 to 0.6, about double the value that people have previously obtained. These values are actually in pretty good agreement with what you might expect from stellar population synthesis models. All right, so now I may have mentioned right in the very beginning, why are we doing all this stuff? And the reason we're doing it is because we want to learn about the properties of the dark halos. And we are getting these properties of the dark halos from the rotation data, and we want to do this rotation analysis correctly, and that's why we've been through this whole saga. So I just want to use the last bit of the talk to talk a little bit about the dark halo scaling laws, which is really what we have been trying to do. Now, when we did this work, this was some work I did with John Cormody a couple of years ago. When we did this work, we used maximum disk decompositions, even though all the indications were that we shouldn't be doing that. And it's been a strange thing. People who do galaxy analysis have, almost without exception, believed, and it has just been believed, that these galaxies are maximal disks. People who do the disk dispersion work have almost universally said you're wrong by about a factor of 2, but it's just the way the subject's gone. We did use maximal disks in the analysis I'm going to show you, and what I've been just saying is sort of justifying this. Now, what we do, the question is, how do the properties of dark halos change with the brightness of the galaxy? Or we could use circular velocity as a proxy for brightness. Galaxies of different masses form at different redshifts, and the density of the universe changes with redshift. So you might expect there'll be some pretty gross changes in the halo properties, and we do indeed see that. The sample includes rotationally supported disk galaxies and also some faint pressure-supported dwarfs. So the total range of galaxies involved ranges over about 20 magnitudes. All of these appear to have dark halos. For the rotationally supported galaxies, we use rotation curves like we saw in the beginning of the talk, and we can measure the central density of the halo, and we can measure a characteristic radius of the halo, and I won't say too much about what that actually means. And we do maximum disk rotation curve decomposition. For the dwarfs, we have to use other arguments. These are pressure supported, so there's no rotation really to measure. We use hydrostatic equilibrium, Jeans equation arguments to get the central dispersion from the velocity dispersion and the baryon distribution, but we can't easily measure these scale radii, which is a pity, but I think we can do this in the future. For the halos, we need some sort of a model, and I won't go through this in in much detail. This is the NFW, one that came out of earlier n-body cosmological simulations. There's distributions with flat cores, which the observers favour, and there's a couple of examples of those. So you can see when the radius is small, the density of the dark halo is pretty much constant at rho naught, and this is just a slightly different version of similar sort of arguments. So the n-body simulations favour these so-called cosmologically motivated halos, where the halo doesn't really have a core. Observations almost universally indicate that the real halos of galaxies have almost constant density cores. And here's a few references on this. We use the isothermal model, which was this one here. So we model the halo with this form, and we're going to try and estimate two parameters for rho naught and a scale radius, which is like this thing. Unfortunately, I've used A for something else in this talk, so excuse that confusion. All right, so measuring the central densities for dark halos of faint dwarfs is a sort of interesting exercise. These are supported against gravity by the stellar velocity dispersion or by turbulent gas pressure. So in these dwarf spheroidal galaxies, they're just very faint collections of stars, but there's much more to these galaxies than you might think. There's underlying this, there's a large amount of dark matter. This is the gassy version of similar galaxies. We think that the difference between these is really just gas content. If these were to lose their gas, they would very quickly start to look like these ones. These dwarfs are strongly baryon depleted, so they've lost almost all of their baryons. Mass to light ratios, instead of being in the sort of range we were talking about, around 0.4, they're up in the hundreds or maybe even thousands. The gravity of the baryons, the gravity of the stars and the gravity of the gas here is pretty negligible, and they're just, the baryons are just test particles in the underlying gravitational field of these dark halos. And we use that as a way to try and use the properties of the baryons to measure what's lying underneath them. And I'll just go through this very quickly. So we need a model for the baryon distributions in order to estimate the halo's central densities. People use sort of ad hoc models, but it really makes quite a lot of difference what model you use, and if the models aren't quite right, you get not quite right answers. From simulations of evolution of small halos, the halos of dwarf galaxies are believed to be rather more extended than the baryons, so these baryon distributions that we saw here, the dark halos are much, much more extended. We assume that the baryons inhabit the core region of the dark halos. The velocity dispersions, when you measure them, of stars in dwarf spheroidals, H1 and faint irregulars, they're roughly isothermal. We're also going to make a simple assumption that these systems are spherical and have isotropic velocity distributions. And we can calculate really in two lines of algebra the equilibrium density distribution of an isothermal isotropic population in the uniform density core of a dark halo. And it turns out to be a Gaussian, and Gaussians project to be Gaussians, and the algebra is very simple. This is the equilibrium, this is the tracer, the pressure equilibrium on one side, this is the gravity due to the dark halo on the other side. Sigma is the velocity dispersion, it's a constant. You can integrate this up, and what you get is a Gaussian coming out of it, and it's got the form like minus r squared over, this is a different A. And if you know A, and you know the velocity dispersion sigma, you can straight away get the density of the dark halo. So it's really pretty much as simple as that, as long as real dwarfs have Gaussian density distributions. Well, do they? And the answer is yes, they do seem to have Gaussian distribution. So here's log of the number of stars as a function per unit area as a function of radius squared. So that should be a straight line if it's a Gaussian, and it's pretty close. Here's a dwarf irregular galaxy. Now we're using H1 as the tracer. It's also isothermal. Looks pretty good. People often use these plumber models. Here's the plumber model, and it's really not a very good fit at all. And if that's not a good fit, then you're going to get the wrong answer for the densities. Okay, here's just another page of faint dwarf spheroidals. You can see they're all pretty much Gaussian. Here's the same thing for the dwarf irregulars, also pretty much Gaussian. So I'm just showing you this because we're going to use the densities that we get for these dwarfs in just a moment. Okay, so when we look at spiral galaxies, this is what we see for the central density of the halos and for the core radii of the halos. So we've got absolute magnitude on the top. So this is just the magnitude of this is just for spiral galaxies at this point. Shows the magnitude of the spiral galaxy going from about -22 to -14. Once you get fainter than about -14, the rotation becomes relatively insignificant. You can't do this reliably. But you can see that there's a scaling here, that the large galaxies like ours have rather fluffy central densities for the halos, down around 1 part in 30 of a solar mass per cubic parsec. As we go to the smaller galaxies, the dark halos rise in the mean by about a factor of 10 in their central density. And so what we're seeing here, we believe, is really just a reflection of the density of the universe at the time these galaxies were coming together. But we'll just come back to that very briefly later. On the other hand, the characteristic radii go in the opposite direction. The big galaxies have large halos, so they're large fluffy halos. The little galaxies have small but rather dense halos. And it turns out with luminosity, the central density goes like about luminosity to the -0.4, core radius about luminosity to the +0.4. If you multiply these two things together, rho naught RC, that is actually a surface density of the dark halo. That's in solar masses per square parsec, not per cubic parsec. And what we see is that the surface densities of dark halos is almost independent of the luminosity. So these very small galaxies, very faint galaxies with small core radii and dense halos have about the same number of solar masses per square parsec as a big galaxy like ours. Curious fact, but I won't have time to go into this, but it has to do with the fluctuation spectrum of the universe that led to the formation of these galaxies. That leads to these sort of correlations. Quite an interesting thing. Now, I've put on here this is the same diagram. I'm just showing you densities now. I've put on here a bunch of these dwarfs. So they're going down to absolute magnitudes of down around about 2. And you can see that they are continuing the trend. The bright one, the faintest of these little dwarf galaxies has got a huge dark matter density. It'll be a tiny galaxy, very dense dark matter, and again, because these little galaxies are believed to drop out of the universe at quite high redshift when the density of the universe was really very much higher. So we believe that these small galaxies have lost most of their baryons, so the absolute magnitude that we see now is probably not a really fair indication of what the absolute magnitude might have been, or if they hadn't lost their baryons. So we try moving these galaxies sideways. We see they overlap in density with the smallest of the spiral galaxies, and so we're just going to shift these at constant density so they get to the line. And so you can see roughly what we finish up with here. And that's the kind of thing, if we shift them by about 4 magnitudes for dwarf spheroidals, just to account for the baryon loss of, say, 25 to 40, that's kind of what we would need to do. This doesn't mean anything really, but it was just an indication of perhaps how much they've lost in their baryon mass because their random velocities are so small. But anyway, you can see the main point of the scaling work so far is that the faintest dwarfs have very dense halos. So we can take a guess at the formation epoch of the faintest dwarfs. The virialized density depends on the collapse redshift Z collapse. According to this little relation, the density would go like roughly 1 plus Z to the cube. The faintest dwarfs have rho naught values about 500 times higher than the large spirals. So the redshifts of formation would then be in the ratio roughly 1 plus z for the dwarfs cubed, 1 plus z for the spirals cubed would be 500, take the cube root, and so it gives you an idea of the collapse redshift for the dwarfs relative to the collapse redshift of the spirals. And what it says then, if z collapse for the big spirals is around 2 to 3, which appears to be the case, then the collapse redshift for the dwarfs would have been around about 20, probably before the time of the epoch of reionization. Okay, so I'm just about at the end. Here's the conclusions from this little section. The pressure-supported dwarfs have the Gaussian density distributions expected if their baryons are isothermal isotropic and lie within the core of their isothermal halos. Dark halos have well-defined scaling laws extending over about 10 magnitudes for disk galaxies and maybe about 20 magnitudes if we include the pressure-supported dwarfs. And the interest of all this is to do with formation epochs and baryon deficiencies. And one of the things that I hope to do in the quite near future is to find a way of measuring dynamical parameters, not just the velocity dispersion, but also for the core radius, not just for the baryons in these dwarfs, but actually for the dark halos from more extended star count distributions. Okay, thank you.
I noticed that your scale height measurement, I think if I read your charts correctly, were obtained in the optical. Why wouldn't you do that at 3.6 microns where you're more sensitive to these cooler, more populous older stars?
Most of this stuff is done either in I-band or in K, so you're sort of on the way, but it's just that nobody's actually done that particular study. Could certainly be done. There's a very big collection of 3.6 micron photography called S4G. Very nice, and I could do this, but just hasn't been done. So we really depend on K-band and I-band, principally for these scale heights.
So I was stunned, actually, that you would measure scale heights in edge-on objects and then do the velocity dispersions in face-on. Obviously, that's optimal for the two measurements, but you're talking about different galaxies.
Yeah.
Is there not some optimal intermediate inclination where you can do both for the same galaxies?
Once the inclination is more than just the tiniest amount, you can't separate the extracting the radial gradient of the galaxy from the vertical one. You've really got to get them almost like the one I showed at the very edge of the galaxy. It's a real pain. So you have to use other scaling laws, and the one most people have used is a pretty tight relationship between the vertical scale height, which is the one you want, and the radial scale height, which is easy to measure, or radial scale length, which is easy to measure. It's got a little noise in it, and it's probably a limiting factor in the solid analysis, unfortunately. Nothing we can do. Yeah.
Josh?
Yeah, that brings up a question. You said in the edge-on galaxies you avoided the dust layer in trying to measure the cold component. Aren't you missing something? Because there's a lot of cold stuff behind that.
Yeah, exactly.
How do you allow for that?
Well, you don't. You just step around it by getting the scale height for the old component, and the spectroscopic stuff we do on the young component we then throw out. We never use it. Yeah.
There's a question in the back.
So we did an analysis like this in Milky Way just for constraining a dark matter disk. And there we found that you do have, in that case at least, you have to take into account all the components. But the other thing is it's not enough just to know the scale height, because as you yourself saw, it changes the shape of the distribution throughout the disk if you have other components. It's going to affect it. So that can be, and if you leave out too much, I think it's different too.
You're absolutely right, that you really want to do these things in at least 2D, but people haven't done it. and it's hard enough to do it just as, and so what we're doing is just a vertical, basically a vertical hydrostatic equilibrium. I think I know the word you're referring to. So we just do it vertically. It's not too terrible because the velocity dispersions even for the hot component aren't very big. But the sort of coupling that you're talking about is significant. I think if one wants to do it really right, one would do that.
Do you have other information at least about the other components, so you could just do a self-effect gas?
No, we're really struggling to
Or can you at least maybe just use it as a systematic and put in a range that you would get if you had other components?
We could, but I mean the errors that we've got already particularly from the scale height estimation and then the whole decomposition process that we do. I mean, those errors are already up around 25% on the surface densities that we're getting, and I think it would probably be comparable with the sort of errors that you're talking about.
So, Roseanne?
No, actually, that was not exactly what I was going to ask, but it came in the core.
Alyssa?
Sort of related question. I think you said that you just use one scale height for one galaxy.
Yeah.
So if there were radial dependence of the scale height, would that make a big difference?
It would, but there was a very nice study done by Alcock and Phillips about 20 years ago, where they really studied how the scale heights change with radius in different kinds of galaxies. And one of the reasons that we use these almost pure disk galaxies is that for those, they found that the radial dependence on scale height is pretty much zero. So, I mean, it's hard enough to get one number here. So, yeah.
So, Charlie?
So with all the information you have on these systems, I guess you can predict the expected vertical height of the cold component, given that you've got sigma for the cold component.
Yes.
Does that agree with
Yes.
the height of, say, from CO measurements of?
Well, I think it would do. And the thing that we just measure out a velocity dispersion for the cold component, and it's the usual 10, 12 number. So I'm pretty sure that we get back the sort of 100, 150 parsec scale heights for that cold stuff. But it's the dispersion that we actually measure.
Melinda?
Do you make any allowance for the presence of hot baryons that you're not measuring in the optimum?
No, we don't. I tried to do something like that when I was solving problem 4.22 at the beginning of I just blown away to find a solution with a hot, extra hot component. It should be possible, but I couldn't do it. I'd have to do it numerically. I could do it for sure. Yeah.
What about tidal dwarf galaxies?
I really don't know about tidal dwarfs. I'm a bit torn. I know there's a pretty strong case for them. And I would just have to say that they are just a torn off baryon thing from other galaxies, but that their formation process isn't the usual dark halo in-form process, but that's not a very good answer.
So I wonder if you have any handle on total masses for some of these systems, which of course does depend on outer radii. So when you jack up the mass of the disk from previous to maximal, maybe a factor of 2. Mm-hmm. But sooner or later the halo component does dominate. So what impact does it have on total mass of the galaxy for reasonable models of the outside?
It probably wouldn't be much because, I mean, for a galaxy like ours, the dark to baryon ratio is just enormous. Mm-hmm. And if you double the baryon ratio, it's not going to make much difference to the total masses.
But it might change the normalization for the dark halo.
It probably would do. But I mean, for our galaxy, the number is something like 95% dark, 5% baryons, but that's already really got most of this physics in it. So for other galaxies, it's probably similar. So I don't think it'll make much difference. Yeah, it changes the baryon budget problem a little bit, but I think for total masses, it's not going to be much.
If there are no further questions, let's thank our speaker again.
Here.